Yeah, so for posterity's sake, this recording will be the derivation for Lab 4 ECE 2245. This is what the Canvas page looks like, and we're going to use these, well, really, we'll use these 4 documents as we go through this video, and I'll be working off of this Lab 4 updated handout. In your own time, it's worth reading the abstract and the introduction here. And I'll just do a quick cursory overview of this. So in Lab 4, we'll be designing an audio low-pass filter. This is a typo, which is funny because it's in the title, but that was super confusing. Last lab, we had to go through a lot of work trying to determine that this is actually a low-pass filter, not a band-pass filter. And you can see, if you look through the table of parts, we'll actually use 2 3.5 millimeter audio jacks on our breadboards. And so we're basically going to have a cascaded system, which you'll see as we work through it. So with this introduction sort of being extraneous information, I think I'm just going to get started, but yeah, please read through some of this stuff when you get a sec because it's worth checking out. So going basically right here, this is the beginning of the lab derivation. And it says, if you read through the lab, in the first week of the project, your goal is to design a Butterworth filter with a cutoff frequency of 10 times, or I guess that's the F sub C, and the omega C is 10 kiloradians per second. And then to accomplish this goal in the first week, you want to complete these different tasks. So we'll go through each of these, and we're going to start with part 1, which is to use the node voltage method to derive equation 1 representing the transfer function of the circuit in figure 1. So we're going to derive H like this, and you know, I'll refer to equation 1 periodically as we write. But let's get started. I think you should all quickly draw this circuit in your notebook. So take a moment to write that out. Oh, and for your information, we'll get to the whole stuff after part 1. So maybe that's 20 minutes. Okay, so assuming you've got this circuit thrown down, let's go over the different components real quick. So there's this node V1 and V out, or this node V out right here, which is connected to the non-inverting terminal VP. We know VP equals VN, and VN feeds back directly to V out. So that's how I was able to identify that this node is V out. And I hope that makes sense. So the first thing we can do to start solving for the gain or the transfer function is to write an equation for this node. And I'm going to ask that somebody just blurts out maybe how we could solve for V out in one word or one sentence. Rather than using the node voltage equation, there's another equation we can use. KCL would work too, but there's a better one. What does, if I said that V1 right here is a source, going from ground to V1 is the source, and if I replaced Z2 and Z4 with resistors so that my circuit just looked like this, what do we usually use to find the out? Exactly. So this is a theme that is going to continue through all of the next courses you take. I think it's 2260. But voltage divider and seeing voltage dividers is a really important skill. So I'll write that V out is just V1 times Z4 over Z4 plus Z2. So that's a really quick and easy way to write that equation. Okay, so let's go ahead. Now that we've identified this V out equation, it's really easy to use node analysis. And give me half a sec, because sometimes we all mess up during the heat of the derivation. I sometimes mess up the fundamentals. But so the way that we go about this, starting with a voltage, node voltage at V1, I'm going to write V1 minus VI over Z1. And then plus, that'll be this feedback loop. I have V out over here minus V1 over Z3 plus V1 minus V out. So, or sorry, V out minus V1 over Z4. So that equals 0. And, you know, this is the sum of the currents equals 0, or node voltage. So let's do the analysis here. This is sort of my approach to node voltage. I don't know if you've all seen this exact approach, but I'm going to start by factoring out my terms. So I'm going to factor V1 out of everything. Or I should say I'm grouping my terms. Wherever there's a V1, I'm going to group it and factor. So I see a V1 on this first term, second term, and the third term. So I'm going to have V1 times 1 over Z1. And then that's a minus. One sec, did I? I'm gonna actually factor V out, V naught first. Sorry, guys. So I see that I have 1 over Z3 plus 1 over Z4. And if I distribute those, this V out, then I would get that fraction right here. 1 over Z3 plus 1 over Z4. So that would handle all my V out terms. Now I'm going to get minus V1. So, because I see that I have a minus V1 on all these terms. Oh yeah, and I did get this first one backwards. I think that's what you were saying. This first one should be V in minus V1 over Z1. Thanks for catching that. So on my minus V1 term, I'm going to have 1 over Z1 plus 1 over Z2 plus 1 over Z3. So I will set that equal to the final term, which is V in, or minus V1, sorry, minus V in over Z1. So I just moved that term over to the other side. Okay, so now I can see that I'm one step closer to getting H. Remember, H equals V out over V in. And with this new equation I'm working with, I can see my only voltage terms are V out, V1, and V in. But I have this equation up here that relates V out and V1. So let's substitute that in. So I'm going to solve for V1. So V1 equals V out times Z4 plus Z2 over Z4. And I can substitute that in right here. which is kind of, yeah, that's the next best step, I think. So in doing that, I'm going to have V out times 1 over Z3 plus 1 over Z4 minus V out times Z4 plus Z2 over Z4 times the addition of all those terms, the reciprocal addition. That's equal to negative VI over Z1. So now I can see that I can easily just factor out my V out term from both of these, and I could divide it over. So if I do that, I would actually get realize that H inverse is equal to V in over V out, and I can easily solve for that right now. So that's going to be, I'll also have to multiply the negative Z1 over, so I'll have negative Z1 one sec, I want to just check something real quick because I somehow did this really elegantly the last time I did this. So I'm gonna follow this same flow for a moment, I think. Yeah. So before solving for H inverse, we could do that, but sometimes it's easier to just group terms when they're in the numerator like this, because if I moved all my terms to that denominator, it's just an extra thing for me to keep track of. So I'm going to factor out my V out and just move that over. So what I'm really solving now is 1 over Z3 plus 1 over Z4 minus Z4 plus Z2 over Z4 all times 1 over Z1 plus 1 over Z2 plus 1 over Z3. And that's equal to negative VI over V out times 1 over Z1. Or this is equal to H inverse times 1 over Z1. So now the thing to do is to start and simplify this left-hand side and see if we can get it to more or less resemble this step over here. And I'll move Z1 over. I'll multiply that up in a second, but let's start to collapse all of our terms and simplify now. So if I get these first two terms, I would have Z4 plus Z3 over Z4 Z3 minus, if I add up all these terms, I'm going to get Z1 Z2, or sorry, I'll get Z2 Z3 plus Z1 Z3 plus Z2 Z1 all over Z1 Z2 Z3. Let me slide that down.
Hello.
Hello.
Hey, how's it going?
Good. We're going over the lab 4 derivation on my Zoom channel right now.
Zoom channel, you say?
Yeah. And yeah, I am recording this, so you can refer to it later if you need to catch up on the first part.
Okay.
But yeah.
You can call it and share if you want to. Yeah.
So I'm just gonna continue to write this out. And like I mentioned, this is kind of a tedious derivation, but we can get through it pretty quickly. So the next step is to simplify this expression. So we're gonna pass everything through. So I'll just write the first term, z4 plus z3 over z4, z3 minus, and then I'm going to have to distribute z4 onto those three components. So that's z4, z2, z3 plus z4, z1, z3, and so on. And then I'm going to distribute the z2. So rather than putting z2 squared, I'm just going to write it out twice. And you'll see why that's nice. Sometimes with these larger equations, it's easy to factor them out when you can see them like that. And in the denominator, we just have our four terms. So that's z1, z2, z3, z4. Okay. So now, now if I want to add on this part, I would have to multiply this denominator by the portions which are not present. And let me make sure I did that all right. Yeah. So it needs a z1 and a z2. So I'll have that in the numerator. I'll have a z1 and a z2 and a z4 plus z1, z2, and a z3. And then I'm also going to have all my previous terms. So I'll write those all out. And I'm sorry, it's atrocious and hard to read, but this is just how I went about it. And then the denominator is going to be z1, z2, z3, z4. Now, remember, up here, it was equal to h inverse times 1 over z1. So if I set it equal to h inverse, that means I multiplied my z1 up here. So my z1 is just out front. And that's nice because I see that that cancels with the denominator, just like that. So here's my new equation for h inverse, and let's go through and we can see that some of these are going to cancel out because, oh, this negative sign is supposed to distribute through all of those terms. So I need parentheses there. Okay, so the way that I like to do this is that I see a positive 1, 2, 4. So that should cancel over here. So here's a 4, 2, 1. It's the same thing. So this term disappears. What about the 1, 2, 3? Here, over here, I see 2, 1, 3, which is the same as 1, 2, 3. So this term also disappears. Okay. And what I'm left with is all these other terms. Oh, sorry, this was supposed to be a negative Z1. So I'll just leave that minus sign out front. And you can see that all my other terms have a negative sign, so that minus sign will cancel. Now what I want to do is look for the parts, like what do all of these have in common? So I see that there's a 4 on 2 of them. What about a 3? It's a 3 on all but that last one. Well, the reason why I'm saying that, my motivation is because I want to get to this circuit. So I see that the numerator will have a Z3, Z4, and we're looking at H inverse. So I have a Z3, Z4 right here, but so I guess that means that my denominator, the Z2 term, has got to go. And I'm worrying now that I might have made a typo because it looks like the Z2 term won't cancel, which is an issue. So give me a second while I look at this. I'm going to go back to my previous solution too, just to verify. Oh, I guess the 413 term. Did I cross out the wrong one? Should have a 314 and a 214. Sorry guys. Oh, I made a typo back up here. This was okay. I think I see what I did. I said that this was V out times Z3 over Z4, but that Z3 is supposed to be a Z2. So let's go through and fix that. Wait, is that right? So this is the node voltage equation from the previous solution. Should be the V out has 1 over Z2 and 1 over Z3. And oh yeah, so V out minus V1 over Z3. V out minus V1 over Z2. That should be a Z2 right here. Wow. Okay, so yeah, so this should be Z2 and Z3. And I think that will put us on the right track. And this is actually not a terrible typo to fix. It'll go pretty quick. So that should be Z2 and Z3. This is a Z3. This Z4 is a Z2. A Z2. Okay, so now what did I need to multiply to add those two denominators? So these first two terms are going to be different. My Z1 will still cancel. One sec. So that'll be, I'm just gonna make a few corrections. Oops. Z2 and Z1. Okay. Yeah, so in order to get these two denominators to be equivalent, I would have to instead multiply by a Z1 and a Z4. So I would have Z2, Z1, Z4 plus Z3, Z2, Z, or wait, sorry. It needs, yeah, so that should be Z3, Z4, Z1. So now I can go back and cancel out the correct ones. So I see 341 and 413. So these terms go away. And I see 214 and 421. So now we're on the right track. My Z1 canceled with the denominator, and my minus signs will cancel. And I can see that each term has a 2. So I'll factor out the Z2. So we'll have Z2 over Z2 times, in the denominator, I'll be left with Z3, Z4. And in the numerator, I'll have Z4, Z3. So I'll factor out a 2 from this first term, plus Z2, Z3 on this term, plus Z1, Z3, plus Z2, Z1. That's equal to H inverse. Now, I see that this is equivalent to this equation. Let's see. So I have Z1, Z2, so that's 1, 2, 1, 3, 2, 3, 3, 4. And here I've got 1, 2, 1, 3, 3, 2, 3, 4, and 3, 4 in the numerator. Yeah, so this gets you H. So I'm just gonna put a check mark there rather than write out, normal H instead of H inverse, but I'll leave that up to you. So that solves part 1. So I'm gonna just take a moment and let you guys write your thoughts out or ask any questions. All right, if there's no questions, let's go on to part 2. So part 2 says, find the Q values for a 4-pole Butterworth filter. These can be found in this document, filteractivebutterworth.pdf, and it's in the same file folder as this lab on campus. Specify the Q value for each pair of conjugate poles. Because there are 4 poles, you'll specify 2 Q values. So we'll go over this all together. So referring to the lab handout, and on this document, find active butterworthfilter.pdf, that's what I'm going off of. So I've actually just screenshotted that content here. And I wanted to give, because I'm sure you're curious what a Butterworth filter is. We should talk about it. So here I will draw the transfer function. So this is H versus frequency. And a Butterworth filter looks something like this, just generally speaking. It's a maximally flat filter in the passband. At the cutoff frequency, we'll call it V sub C. It decays mostly linearly over the phase transition. And then it has a maximally flat reject band too. And when I say maximally flat, oops, sorry. When I say maximally flat, it means that there might be some ripples actually. So maybe it's not a straight line in the passband, but it actually ripples as a function of frequency. There's a lot that goes into actually designing Butterworth filters, and it's something that you'll learn about if you take microwave engineering, and they also probably come up in audio engineering. The design process of Butterworth filters involves a table where people experimentally found certain solutions. There's a lot to say about actually deriving like Butterworth filter equations, and it's not something that people really do nowadays. Most people just use software to make a Butterworth filter. But if you're curious about that, we can talk about it more perhaps after. So yeah, let's just quickly review what this talks about. It's a maximally flat in the passband, has a nearly linear phase response. This means that the waveforms are better preserved. And for this reason, the Butterworth filter is a good choice for filtering of speech or music. So it's great for audio circuits. Yeah. All right, so getting into the actual details, the poles of a low-pass Butterworth filter lie on a circle of radius omega c in the left half plane in the S domain. That means poles are located in the nth roots of -1, and they follow this sort of equation. So let's draw out sort of what that looks like. And real quick, this equation's great, but the way that I kind of think of it is that the poles are going to be located at e to the j theta. So there's going to be multiple theta values for the poles, and they'll have some radius. In this case, it's a circle of radius omega c, so we would put omega c out front. So the poles will look something like this, and we'll plot these on a unit circle. So I'm going to throw out real quick a unit circle. Okay, so looking at the fourth order Butterworth low pass filter here, it has this following transfer function. And really what I see is S minus a complex number times S minus its conjugate. Does anybody know how I identified it as the conjugate? Yep, so I can see this negative sign on the J. I'll zoom in a bit right there. So the other end is the same thing, right? It's S minus a complex number times S minus its conjugate. Let me highlight those. Okay, now notice that the angles here, we have 4 angles, right? We have plus 5 pi eighths, minus 5 pi eighths, 7 pi eighths, and minus 7 pi eighths. So I can draw those on the unit circle, and they look something like this. This would be approximately theta equals 5 pi 8. This is approximately 7 pi 8. This is minus 5 pi 8. And this is minus 7 pi 8. And I was able to observe that these are the locations of my poles directly from the transfer function. Now, it's kind of difficult for us because this is just something we're given. It's not something that we have this deep theoretical understanding of how to derive this function, but it's what we're going to pick up and run with in this lab report. And so just to clarify, in part 2, it asks us to find the Q values, in part 3, it says using information in the Butterworth filter PDF, specify the locations of poles for your Butterworth filter. So I'll write this answer. The locations are at theta equals 5 pi 8, 5 pi 8 minus 5 pi 8, 7 pi by 8, and minus 7 pi by 8. So that's what you will use for the locations of your poles. It also asks us to specify the Q values in part 2. So let's go and find out what those are. So here they are. Okay. So I can see that generally Q is equal to omega C by alpha, where alpha, we'll come back to what alpha is later. You've actually seen alpha before, but identifying alpha inside of our function, it's the real component of the complex number. So I can write out, you remember we're working with this, the pole looks something like this, omega C e to the j theta. And that's equivalent to saying omega C times the cosine of theta plus j times omega C times the sine of theta. So this is the real component, which is alpha. Now it's also going to be equal to 1 over r c. I think we'll come back to that, but this is the same alpha from the RLC equations. We just don't notice it yet. But anyway, so I can see that if I plug that in, I have omega C over omega C times the cosine of 5 pi 8. If I want to write out Q1, and so that's going to be equal to 1.31. And sorry, this should be 1 over 2 alpha, so there should be a 2 in the denominator. So for Q2, we get the same thing. Instead, though, we have Q2 is equal to 1 over the cosine of 7 pi 8, which is equal to 0.54. So those are the two Q values. Now notice that because the cosine is an even function, if I plug in plus 5 pi 8 or minus 5 pi 8, I get the same answer. So that's why there's two Q values. It's because the denominator is an even valued function, an even valued periodic function. And so even though there's 4 poles, there's only 2 Qs. So a quick little discussion as well. This might be your first time seeing a pole. So I'll try to kind of draw out what this concept is. But if we looked at our function in 3 dimensions, where the z-axis is h and the x-axis is frequency, and I think the third axis is time. It doesn't really matter, but with a 3-dimensional function, if I had something like h is equal to 1 over 1 plus alpha, then if alpha equals -1, h is infinity, right? And so we'll say that this is alpha equals -1. So maybe this axis is the alpha axis. I'm not sure. Anyways, at that value, we would have an infinite point. And so in 3 dimensions, everything would tend away from it, and it would have this sort of shape. And that's why it's called a pole. This is so dumb, but it's the truth. It's because it looks like somebody took a blanket and stuck a pole under it. So that's actually why that's referred to as a pole. Now, maybe a more justifying reason is because poles are sort of like the northern and southern hemispheres of something, north and south pole. I don't know, but this is what I was always taught. So there's your silly intuition for what a pole is and how to identify it. It's the denominator of your function. Okay, so part 2 asked us to find the Q values, and we did. So Q1 equals 1.31, Q2 equals 0.54. I think let's just double check that from the document. Yep. So that gets us through section 2, 3, and section 1. Okay, so the last part for today that we need to get through is part 4, and it says based on omega C and Q, can you find resistor and capacitor values for a sallen key implementation of the filter? Sorry, I actually have no idea how to use OneNote anymore. Okay, thank goodness I found my way back. Says for guidance, read the document provided in the lab handout. And then for each section, we'll get to this, there's 2 sections. Specify the values you plan to use for R1, R2, C1, and C3. So in the lab handout, filter active sallen key.pdf, this is the document that I'll be referring to from now on. And I took screenshots of this as well. So here they are. So let's go through the document. So this is the normal sallen key filter. It's actually sallen keys, if I'm not mistaken, are a subsect of Butterworth filters. So that's why we were discussing Butterworth filters. It says that multiple sallen key filters in series are a convenient way to implement higher order active filters. So this is a 2-pole filter, but if we put 2 of them in series, then we can have a 4-pole filter. So one of the filters will be 5, it will have Q1, and the other filter will have Q2, if I'm not mistaken. Okay, so there's the transfer function of our filter. And it says that the sallen key in figure 2 implements a low pass filter. So this is our new circuit for our sallen key filter. So moving back here so I can continue to write. We know that the impedances of Z3, which is this item, so that's Z3, it has the impedance 1 over SC1, and Z4 has the impedance 1 over SC2, which I'm sure you guys can identify based on the previous discussions in this course. So it says that the circuit transfer function becomes this value. And so now it's up to us to show that that's actually what we have. So just a moment. So let's take our existing transfer function. So what was it? It was H equals Z3, Z4 over, I'm gonna just write it all out. So that's Z1, Z2, Z1, Z3, Z2, Z3. So that's Z1, Z2, Z2, Z3, Z3, Z4, I think. And Z2, Z3. Okay. Oh, wait. I'm missing Z1, Z2. I'm just gonna screenshot it because, yeah. Anyway, so we'll take H and we'll plug in these Z values. That's kind of where I'm going with this. So Z1, Z3. That's what I was missing. So we can plug in our Z3 and Z4 in the numerator. So that's 1 over SC1 times 1 over SC2. That's Z3 and Z4. Z1 and Z2 are now R1 and R2. So that's just the impedance of a resistor is just the resistance. So that's that term. Now plugging in Z2, that's R2, and Z3 is 1 over SC1 plus Z3, Z4, that's this term again, 1 over S squared C1, C2. And then plus Z1 is R1, and Z3 is 1 over SC1. Yeah, this is correct. So there's a few things I'd like to point out at this juncture. The first thing I want to point out is kind of cool that this function we came up with for H, notice it contains one impedance term for every part of the circuit. So it handles all of these components 1, 2, 3, and 4. So there's a term for every component. And notice the denominator is sort of like the sum of a bunch of these things added up. And the numerator just contains components 3 and 4, which are the only components directly connected to this node. So that's kind of cool to point out that there might be some sort of deep mathematical intuition you could come up with to just write this output on the fly rather than using node voltage. Okay, the next thing I wanted to point out with is after we plug in circuit values, RLs and Cs, we're left with an RLC circuit. And what I mean by that is that this function closely resembles everything we've done in this class up to this point. So we can kind of just use the same approaches that we have before. So the first thing I'm going to do is I see this term. I see that my denominator has this quadratic term S squared, and it has this SC1 and a term out front. So I'm identifying that my denominator is a quadratic function. And so what I can do is start to group stuff to make it easier. So if I multiply the numerator and the denominator by 1 over S squared. Oh, sorry, one sec. I want to make sure I don't veer too far off the path. But yeah, so basically we just need to start factoring stuff out. So if I pull out this term 1 over S squared C1, C2 from each term in the numerator and denominator, in my numerator, I'll just have 1. In my denominator, what do I get? So here I have the 1 over S squared C1, C2 term. So that will just become 1 plus I'm going to have an R1. If I pull an S out, one second, I'm kind of confusing myself. I think this is right. Sometimes going through these long derivations, I get a little backwards with my algebra. Yeah, I should have just SR2C2. So yeah, the idea is obviously that if I distributed that back through, that I would get the same. If I distributed s squared c1 c2 through, I would get this same term right there. Oh, so but instead I should have a c2. So r1 s c2, and then I'll also have plus r2 s c1 or c2. That's right. And then plus r1 r2 over sorry, r1 r2 s squared c1 c2. And I think I did all those steps correct. I just, for some reason, that step's always hard for me. But yeah, so we end up with this equation. SR2. Yeah. Let me just go back down. Yeah, so, okay. So let's rewrite out what we have now. So it's 1 over s squared, r1, r2, c1, c2 plus s times c2 times r1 plus r2 plus 1. So this is our final function. And now it's extra clear that we have a quadratic in the denominator. And this is something that we kind of know how to solve. So this is my term for h. Now what we want to do is show that h is equal to this thing up here. And sorry, I keep flicking back and forth between these, but oh yeah, so now we just kind of have to identify what each of these terms are. So I should also have I can see that if I pull out r1, r2, c1, c2 from those things, then I will. Yeah, I made a mistake while distributing those, so I'm just going to write out this is how we want to factor it. Just because I don't want to go and factor those through again. Sorry, that step is always kind of a pain. But so all I did in those two steps is get my s squared term isolated, basically, so that it would model and represent this same function we see right here. So now in my denominator, that's what I've got. So I see that my numerator term has this 1 over c1, c2, r1, r2. And that term, 1 over that, is the same as this last term. So that's my omega c squared term right there. So omega c squared is equal to that term. I can see that I have this 2 alpha s term. So here's my s term. So if I add those together, I would get r1 plus r2 over r1, r2, c1 times s. So this is supposed to be equal to 2 alpha s. So I can see the s's cancel. And then alpha equals 1 over 2 times r1 plus r2 over r1, r2, c1. And notice that all the resistance terms, that actually to me looks like a parallel resistor, r1, r2, it's the inverse of that, right? So the parallel resistance of these two resistors would follow this equation, R1, R2. Oh. Over the sum. And so what I have here is 1 over C1 times 1 over R1 in parallel with R2. And notice this is, we just solved for, but by basically setting the denominator to be a quadratic and solving for the term connected to S, we came up with alpha equals 1 over 2C times R Thevenin. And you may or may not remember this from the first lab, but this is generally the case for our RLC circuits. So that's pretty cool. This is this deep concept in this course that RLC circuits have this sort of quadratic function going on there. So pretty exciting, I thought. I don't know. Okay, so now we can see that if we set the denominator equal to 0, and basically we solve for the solutions of the quadratic function, we actually get this term. So from now on, I'm just going to refer to this equation for H because we found all those terms. So this is what H equals. So if I want the poles, I would set the denominator equal to 0. And as I'm sure you all know, if I want to find the zeros of a quadratic function or the solutions, I use the quadratic formula. So S, what is it? S is equal to negative a plus or minus the square root, all of that nonsense. So here, or that's negative b. So the b term is 2 alpha. So that's negative 2 alpha plus or minus the square root of b squared or c squared.
B squared.
Oh yeah, it is b squared. But why does that end up being a negative up here? We'll get there. Negative b squared minus 4. A is just 1 and c is omega c squared. And then this is all over 2a. So all over 2. So I see the 2's cancel. So this should be b squared.
It can't cancel unless you factor out a 2 from the quadratic.
Right. Oh, and also notice this J term out front. I think this is why where the negative comes from. The J only is going to occur if omega c is greater than alpha. Then we would end up with a negative value in the a negative value inside the square root. And then that would become an imaginary number. So that's where this minus alpha squared is actually coming from, I believe. So if we wrote out the quadratic formula, it would really be 2 alpha squared. That's b squared minus 4 AC. And so that's omega c squared. Yeah, I'm not sure exactly how to get rid of that 4 term now that I'm looking at it. Because this would look something like that. So that Oh, the 4 would come out of the square root and it would be a 2. And then there would be a root 2 on that alpha term. Oh, but alpha also has a 2 in it. Am I thinking about that right?
Yeah, I see where you're going.
Oh, no, I'm so silly. This is 2 alpha squared. So there's a 4 there as well. So when we factor the 4 out, we would end up, all the 2's would cancel. And so what we really are left with is negative alpha plus or minus the square root of alpha squared minus omega c squared. And if this condition is true, I didn't know I could do that. But sorry, if this is true, omega c is greater than alpha, then this term, we should flip it around and we should pull out the imaginary number. Because, yeah. And anyways, I'm not going to spend any more time analyzing this really, but so that's how they were able to say that in the document, it follows that the poles of the filter are located at the solutions of that quadratic formula. So, and yeah, just to kind of really round this out, this document also has the solutions for alpha and omega c in case you forget them. And the big concept here, in my opinion, is this idea of the quadratic formula showing up in RLC circuits all the time. Okay, so from here, we are actually finished. The document says that there's this neat simplification method you can go through. It doesn't really simplify it, but we'll just discuss on screen what they did here. So they say if we use this function, R2 over R1 equals little r, and the ratio of the capacitors equals little c, then we can plug that into our parallel resistance and get new equations for alpha and omega c. We can plug those into Q, and then we can also solve those, we can solve that equation for Q for this ratio of the capacitors. So that's what they did, and it's one approach for sure. But from here, we basically go about finding our actual values for our resistors and capacitors based on Q. So let's do that with the equations that we have written. And it's the same approach either way. But so we know, for example, Q1 equals 1.53. And that's equal to omega c was 1 over the square root of R1, R2, C1, C2. So that's our numerator, and our denominator is 2 times alpha. So that's 1 over, sorry, what was alpha? You just wrote it up here. 1 over 2 C1. So that's oh yeah, because we have 2 alpha in the denominator, and alpha is 1 over 2. That's all that. Yeah. So I guess the concept of using the ratios is just to show you that, like, it's a little complicated, but as it turns out, there's infinite number of C1 and R1 values that would satisfy this equation. So we just need to pick one. So for example, let's say that R2 equals R1. We'll say that this condition is met, or, you know, the ratio equals 1. If they're equivalent, then I can start to go and factor stuff in here. So then I would get that 1.53 is equal to 1 over, we also got to choose a similar relationship for C1 and C2. So let's say that C1 equals C2, or that C2 over C1 equals 1. So we chose these two criteria. So if that was the case, then I would have 1 over the square root of R1 squared C1 squared in my numerator. In my denominator, I would have 1 over C1 times, this would be 2R1 over R1 squared. So I'll just start to simplify that. The numerator becomes this. The denominator becomes this. And I see my R1s cancel, so then I get wait, did I make a mistake here? So this looks like everything cancels out. And it's also an inequality, so I must have made a mistake somewhere. Anyways, this maybe I will refer to the equation that Neil wrote. This approach works. It's a little bit trickier in some regards than using these ratios he comes up with. So he took Q and he solved for C, little c, which is equal to C2 over C1. And then, yeah, he just chooses different ratio values, which end up allowing you to solve for these different capacitors and inductors. So using this equation 9, we could say that C equals 1. And that's equal to 1 over 1.53 squared times, we'll say that R equals 1 as well. So that would be 1 over 1 plus 1 squared, so 1 over 4. I might be running into, I might be severely confused for a moment. Because I mean, just plugging this in, like I know that 1 is not going to be equal to that, so that's why I'm confused. But I also know that this works, so because then we would get this equation that C2 is equal to C1 times 1 over 4 times 1 over Q1 squared. And that should be correct, but I'm just confused why there's this inequality right here. Something's going on there. And in the interest of time, I think we should come back to it maybe outside of the recording, but there's one other tool I wanted to show you, which is on the lab handout page. They give us this Excel spreadsheet where they actually coded in all of these equations. So I'll show you what that looks like, and you know, some of you may not be familiar with Excel, so I'll show you kind of how to use this a little more detail than it's provided. So here's the Excel spreadsheet, and you can actually go and click on any of these cells and it will tell you how it's calculated. So I clicked on this top cell and it shows me the various values that come into play and how to come up with this equation. But so he said that C is that equation, which is provided in the handout right here. That's the same equation. And notice he's got basically, Neil has put down the same calculations in two different areas. So I can see that this column is the same on both of them. You can see that this column's also the same equation, but the only thing that changed is they use Q2 here instead of Q1. So there's my Q's that I can go and enter, and that changes this column. D is the square root of 1 over RC1, where C1 would be calculated from that ratio. And then R1 C1 times 1 million is calculated right here. Anyway, so we want to use this. Let's choose a resistor ratio. We'll say R is equal to 1. Ah, I see. This is my hang up. So now we have our resistor ratio. We can go and calculate the capacitor ratio is this. So that is to say that C2 is equal to C1, which is equal to 0.146 C1. So now that I have this ratio computed, I can just go choose a C value. So if I say C1 equals 220 picofarads, because I think that's one we have in the stock room that's both affordable and it has like a reliable value, then C2 would just be 0.146 times 220 pico. So it's like a tenth of that. So maybe it's something like, I don't know, 40 picofarads or whatever. And we chose the resistor value, the resistor ratio equal to 1. So I could just use two 10K potentiometers. And then I could tune them to get the most accurate result. Or you could just use two 1K resistors too. So either of those would work fine. And that's how you go about using this sheet. But as I mentioned, the equations are pretty straightforward too, now that we've kind of seen how to use them. Did anyone need those drawings back? I can these annotations. Yeah. Okay, so I think that gets us through more or less all of the things that are asked for in week 1. Let's just review that real quick. So we were asked to find H, we solved for H. We were asked to find the Q values and the locations of the poles. And we were asked to find R1, R2, C1, and C2. So I've shown you how to use those tables to find these component values. You need to do it for Q1 and for Q2. And I'll let you all do that on your own so that you can use this table in whichever way you like. Are there any questions before I close the recording? Cool. Well, yeah, I'm gonna stop the recording then.